Good morning, everyone, and welcome back to Math 365 PDE. So, we were right in the thick of things last time. We're solving Laplacian u equals f with u restricted to the boundary of our circular domain. Oh, sorry, Laplacian u equals 0 with u restricted to the boundary of our domain equal to function f of theta. We were assuming that we were in polar coordinates already. U is a function of r theta. We're using the separation of variables technique. This D is a disk. I started out going on unit disk. I guess the book likes disk of radius r. It doesn't matter one bit, but just to be consistent, I'll work on a disk of radius capital R, just so we can be slightly more general. That hasn't come in and affected any of the calculations yet, because we haven't looked at boundary values. We did separation of variables. We said, let's look for product solutions of the form g times y, g a function of theta, y a function of r. We came up with this first equation, g double prime equals minus lambda g. We looked at these implied boundary conditions due to polar coordinates. That g of 0 must be g of 2 pi, that g prime of 0 must be g prime of 2 pi. And I was a little bit thrown for a loop last time that the individual eigenspaces had, they were dimension 2 instead of dimension 1. And the reason for that is that this is not a Sturm-Liouville problem. This is not a Sturm-Liouville problem. You look at these boundary conditions, it's not a times g of 0 plus b times g prime of 0, right? It's two conditions on g, or like one equation on g and one equation on g prime. If it were a Sturm-Liouville equation, then each eigenspace would have one linearly independent function. But it's not. And so what we learned was that in this case, our lambda was positive, and in fact, it had to be n squared, where n was allowed to be an integer. So, I mean, lambda was positive or 0, right? The case where lambda was 0 just gave us constant function g of theta equals 1, and this is your basis for the lambda equals 0 eigenspace. Computer's doing something. And for lambda bigger than 0, lambda had to be n squared for n in z. And so for the lambda equals n squared, what was the basis for the eigenspace? If you let complex basis, then you just get e to the I n theta e to the minus I n theta. So these are the two linearly independent solutions to that equation with these boundary values with lambda equals n squared. Straightforwardly, right? Just take two derivatives and out comes n twice, out comes negative n twice, giving you n squared. Now, if you want to write this in terms of a real basis, then you could do cosine n theta and sine of n theta. Either of those two options are available to you. And I'll just kind of leave it at that. So these are connected, of course, by Euler's formula. This is cosine theta plus I sine theta. This is cosine theta minus I sine theta. So in this case, you can split this up as one solution per n. In this case, you're really getting, and I guess my implicit assumption here is that n is bigger than or equal to 1. So in this case, you're getting one solution for every integer, truly, and in this case, you're getting two solutions for every n bigger than or equal to 1. But it's the same thing. That's what was happening last time. And what else? So we solved the equation for y, this Cauchy-Euler equation, and we learned that for n equals 0, for lambda equals 0, we once again got y equals 1 as the single basis function for that eigenspace. We're looking at this r squared y double prime plus ry prime equals minus n squared y solution. And we also said, well, okay, so what about lambda equals n squared for n being any integer, and the basis for solutions was r to the n and r to the minus n. So the vector space of solutions to this problem is spanned by those two functions, if you like. But we're only interested in those solutions that don't have a singularity at the origin. So that means when n is positive, you throw out this one. Or in general, you only consider the solution y equals r to the absolute value of n. So regardless of your integer value, you're interested in that solution because you don't want to blow up at the origin. So this naturally gives you one independent solution per n. And even when n is equal to 0, this kind of naturally fits into that one. So it's kind of more natural to take the complex version because you get just this e to the I n theta for any n in z, and you get r to the absolute value of n for any n in z. You multiply those products, add them up. And so you get that your product solution looks something like r to the absolute value of n times e to the I n theta, where now n is allowed to be any integer. And so you're saying now that by separation of variables, you just want to add them up. Linear combinations, like infinite linear combinations. So Cn times r to the n times r to the n theta. And so this is your general form of the solution. And you can also write this another way. It would have to be, yeah. You could also write this another way. You could write this as u is equal to a naught over 2 plus the sum now goes from 1 to infinity of like an cosine n theta sorry, an. So still r to the n. Still r to the absolute value of n, but now n is positive. So an cosine n theta plus bn sine n theta. It's really the same. It's 100% the same. It's just the difference between complex. Find the difference between these two pictures. Right? There is none. It's really the same. It's just you're just picking the two different bases for the same vector space. You can think of it that way. And we spoke about that when we talked about the difference between complex Fourier series and real Fourier series. The only salient difference is now you've got this factor of r to the n in there. And usually we had something like an exponential that became 1 when we plugged in our boundary value. But this time we've got something different because our condition was like f of theta is equal to u. Well, you plug in r equals capital R. So if I were on disk of radius 1, I'd plug in 1. In general, plug in capital R. And so instead of this usual Fourier series, you're getting Cn times capital R to the n times e to the I n theta, telling you that your Fourier coefficients will be modified by 1 over r to the n. In fact, you can see that here, because if you take the linear algebra inner product, f inner product with e to the I n theta, and so now you do need that complex conjugation, like you say, then this will be what? So it'll be Cn r to the n, capital R to the n, and then you'll have the inner product with e to the I n theta with itself, and this number is equal to 2 pi. You've seen that calculation before. But I'll show it anyway, I guess. So you're going from 0 to 2 pi and e to the I n theta, and this one is e to the minus I n theta. Right. Because this L2 inner product for complex functions, you have to put the conjugate on the other factor. And so you're just integrating 1 from 0 to 2 pi, which is telling you now that C sub n has to have this formula. It has to be 1 over 2 pi times capital R to the n times integral from 0 to 2 pi f e to the minus I n theta d theta. Any question on that?
Yes. There is a question.
Yeah.
Where is F in this inner?
Where is f?
Inner product of F e to the I n theta.
Yeah.
Yeah. And then shouldn't it?
So I'm taking this equation, and I'm taking the inner product of both sides with e to the I n theta. So here and there, and here every term drops out except for the one.
Oh, I see.
I mean, more formally, you might, to make it more clear, you might reindex this with m, and by orthogonality, you only get the one term. Okay, cool. And I mean, you can also do this with that version. You can make formulas like your usual formulas for Fourier coefficients that will also correspondingly be modified by 1 over r to the n. See your textbook for that derivation. And so, like, to this point, we've basically just been declaring ourselves done with the problem when we say this and that. And this will be well defined, by the way, for any function f that's even in L1. And it was a little bit of a miracle that we got here because, I mean, we just had the one solution for each n, and when we took the product, it happened to be true that we had this nice complete orthogonal system that was given to us, even though that wasn't guaranteed by the theorem, because we did not have Sturm-Liouville theorem to fall back on. But I want to do something more. I want to work and actually show you a real formula for the solution. That's what I want to do. And in order to do that, so keep this in mind. Let's work with the complex part. In order to do that, I want to investigate this series. This complex series. So this will turn out to be somewhat of an analog to when we did the Dirichlet kernel and realized Fourier series partial sums in terms of a convolution. Here I'm going to get a formula for this expression, which will allow me to, after substituting this formula for the coefficient into the expression for u, it'll allow me to replace this with an integral and then finally arrive at a formula. That's what we're going for. So what I want to do first is find a real expression for this thing. So I said real expression, and I really meant it. So is this a real number or not? Like for any theta, is this a real number or not? So if I take the complex conjugate of this, complex conjugation is linear and continuous. So for like this absolutely convergent series, it'll be true that this is r to the n times e to the minus in theta, right? In other words, I bring the conjugation to the inside, then bring out the real number, and I'm just left with e to the minus in theta. But this is back what I started with, right? This amounts to nothing but a rearrangement of the terms, because for every negative n, there's a corresponding positive n. So, right, and for absolutely convergent series, you can rearrange the terms like that. So long as this r is less than 1, that you can do all this. So yeah, here it comes. This is not your cat. This is a real number. And so I always, of course, prefer to keep it real. So that's my complex outfit. And so this is yeah, let's just stop there. That's great. Okay, yeah.
What did you just break down? You just took the complex conjugate.
And showed it was equal to itself.
But you already wrote that it was equal.
No, I took the complex conjugate of this,
Yeah.
which is equal to this series with the complex conjugate over this part, which is equal to e to the minus in theta.
Okay.
And e to the minus in theta, I'm summing up over all integers, positive and the negative. So this is just rearranging the terms. So it's the same thing as this one.
Oh, I see. That bar is important.
The bar is important. That's complex conjugation of the number, yeah.
What is that?
N is an element of the integers. You're summing over all the integers.
I know, but how are you supposed to draw it?
Draw this.
No, the term on the right.
I don't understand.
Like the symbol for integers.
It's a Z.
Instead of it, it's a Z.
Yeah, yeah. This is called Blackboard bold font.
I see.
Yeah, and Z is the standard way. I mean, not to beat a dead horse, but to explain this more, these are the partial sums, right? And so if I put a minus sign here, that's just like writing the positive, that's like writing the ones with positive n first, and then the ones with negative n. Whereas for this finite sum, it's just like writing the negative ones first and then the positive ones. That's all. That's all. If a complex number is equal to its conjugate, that means its imaginary part is 0, and that means that complex number is real. So this is real series. Okay. The next thing I want to point out, this is actually kind of a complex argument. I'll stop. Okay. The next thing I want to point out is the following. So ultimately, we want to find the sum of a series. And so what does it go back to? Yeah, Calc 2. It goes back to geometric series, right? That's like our bread and butter here. The problem, of course, being that this, like I can write z equals r e to the I theta. This is the complex form this is the polar form of a complex number. I lost the pen on the screen. We've got oh yeah, Bill was pointing out should have had absolute value of n in my formula for Cn. Maybe you dropped the absolute values there. So check that. So geometric series, the problem is like this is not the sum of z to the n, right? Because of the absolute values. That's the issue. So we just need to do a little bit of massaging to make it work out. But we will go with this formula for sum of a geometric series. So you know that 1 over 1 minus z is the sum from n goes from 0 to infinity of z to the n. So here with z equals r e to the I theta. And if I multiply both sides by 1 plus z, what do I get? Well, let's just see. So n goes from 0 to infinity, z to the n plus, and so this gets multiplied by z, so this is like, n goes from 1 to infinity, z to the n, right? It's multiplying every term of the series by z, starts the index at 1. So this is like 1 plus 2 times n goes from 1 to infinity, z to the n, right? So not too much more than some algebra there. And so 1 plus z over 1 minus z is equal to this series, at least for those z for which this series absolutely converges. So z with modulus less than 1. And therefore, their real parts are the same. You know, if two complex numbers are the same, then their real parts are the same.
Given that z is less than, oh wait, no, I mean, that's always true then. These real parts will be the same if z is less than 1. The modulus of z is less than 1.
Well, yeah, but that's just because when these two things are equal, like, you know, really all I'm saying is this. So if a plus bi is equal to c plus di, then a is equal to c, right? Then there's nothing to it. But yes, it's true that series only converges when the modulus of z is less than 1. And that's the continuing context in which we're having the discussion. Why care about that? Because I want to look at this series and I want to split this up as n equals 0, n is negative, and n is positive. So for n equals 0, I just get the number 1, right? For n is positive, I get r to the n, e to the I n theta, which is nothing but z to the n. And for n being negative, I'll still index it as n going from 1 to infinity, but now I'll just sneak in negative n e to the minus I n theta. And so absolute value of negative n is just same thing as absolute value of n. So this series, so follow me on this one. So this series is equal to its real part. That we learned earlier. This series is for every theta, you get a complex number that's equal to its real part. And so therefore it's equal to the real parts of, and taking the real part of something is linear, so it's equal to the real part of 1 plus the real part of z to the n, plus the real parts of this. And so here's my big point, is that the real part of this is the same as the real part of the sum z to the n. So when you sneak in this negative sign, you're changing the sign of the imaginary part. You're not changing the sign of the real part. So the real part of this is the same as the real part of that. That's the point. So this series is equal to its real part, which is equal to the sum of the real parts, which is equal to, therefore, the real part of 1 plus 2, and goes from 1 to infinity of z to the n. You're just using linearity again, and this is now equal to the real part of 1 plus z over 1 minus z. So that's the point. That's the cool thing. And I'll put the conclusion. So the real part, 1 plus z over 1 minus z, is equal to the sum r to the absolute value of n, e, I n theta. I mean, it seems like magic, but it's really just the algebra to account for the fact that you're using the sum of a geometric series going from 1 to infinity. And you have to take into account the absolute value. So you need to break it up into two different terms, and then the two different terms have the same real part, and so you get the result. Pause for questions and comments there. Yeah.
Why can we go from integers to the sum of 1 to
So I'm adding up every single term. N equals 0, all the positive n, all the negative n.
That last term is just z and bar.
That's true. That happens to be true.
So that's the negative n's.
Yeah.
Because
R to the negative n, e to the I negative n theta.
oh, okay. Okay, that makes sense. Then for the positives, we showed that that's true.
For the positives, this is just.
Oh,
I-
this is the same. I see.
yeah. So these two terms are not the same, but the real part is the same, because as you mentioned, William, conjugation only changes the imaginary part, not the real part. And then, since the series as a whole is equal to its real part, it must be equal to the real part of this, which is the real part of 1 plus c over 1 minus c. It's actually a really cool argument. So this was the mind-blowing thing that we were going for. And last night, I said, go ahead and calculate this real part. And so if you did that, you may already know the answer in terms of r and theta. But if you didn't, the classic way to find the real part of a number, so you want to multiply by the conjugate. So you want to make the denominator a real number. So you multiply by its conjugate. The conjugate of 1 minus z is 1 minus z bar. Once again, z bar is a minus bi. I really don't. I really want to multiply by the conjugate of this number.
Oh, right.
Yeah. And so you can do the algebra, and on the denominator, you'll get the modulus of 1 minus z squared. So that's this formula that z times z bar is equal to its modulus squared. But here the complex number is 1 minus z. And on top, you get 1 plus z times 1 minus z bar. So what do you get? 1 plus z minus z bar, and then minus zz bar, which is, again, modulus of z squared. So working with complex numbers a little bit. And now you can start plugging in, right? So you remember z equals r e to the I theta, and so 1 plus z is going to be 1 plus 1 plus r cosine theta plus I r sine theta. So on the denominator, you're getting real part squared plus imaginary part squared. So 1 plus r cosine theta squared plus r squared sine squared theta. That's what the modulus squared of a complex number is. It's a squared plus b squared. Calculated that a is 1 plus r cosine theta, b is r sine theta. Minus z bar. Minus z bar. Yeah, thanks. And so, yeah, on top we get 1 plus. So what's z minus z bar? So you're going to get a cancellation, right? If z is r cosine theta plus I sine theta, and z bar is r cosine theta minus I sine theta, then z minus z bar is therefore 2I sine theta. And then you're subtracting now modulus squared, so that's r squared. The modulus of r e to the I theta is just r. Yeah.
What does modulus mean?
So the modulus of a plus bi is equal to square root of a squared plus b squared. It's the length of the vector in R2. And so take the real part of that. I did this multiplication and division thing so I could cleanly identify the real and imaginary part. And this is the imaginary part. So taking the real part is now 1 minus r squared over that, which is what? 1 minus 2r cosine theta plus r squared. Just cosine squared plus sine squared equals 1. Maybe plus, is it plus? Oh, 1 minus z. So 1 minus z is this minus that. So it's a minus sign. And therefore, a minus sign there. Say what?
Is it 1 minus z hat or 1 minus z as it's right there? I mean, not hat z bar.
It's 1 minus z.
Right here. If that's 1 minus z, shouldn't that be negative?
Yeah, sure.
Oh.
Yeah, you're right.
I guess that doesn't change anything though.
Yeah. So a plus b, a squared plus b squared. That's all. Okay, and so how do you actually use this to solve the problem? or to simplify the formula for the solved problem. Remember those advertisements for Glade plugins? Just plug it in, just plug it in. Yeah, just plug it in. Remember, this was our solution. The sum over all integers of C sub n and r to the absolute value of n, e to the I n theta, where C had this formula. Yeah, you were there. So some initial condition. So Cn is just what it is, right? So Cn is like, did we figure this out to be 1 over 2 pi capital R to the n times this integral? F of theta e to the minus I n theta d theta? Yeah. So just to be clear, that's Cn. Yeah, so I just want to plug all that in. So this is uh, 1 over 2 pi, and yeah, with Bill's comment, so there's an absolute value sign there. And this is r to the, this is integral from 0 to 2 pi. Or I mean, we're multiplying also by little r, absolute value of n, and we're integrating. And I'll change, this is theta here, so I'll change the variable of integration to t. So e to the minus int dt all times e to the in theta. So that's nothing but direct substitution of Cn into the formula. And so I can bring this e to the in theta inside the integrand. And I'll end up with like 1 over 2 pi, and I'll write this as r divided by capital R to the absolute value of n, integral from 0 to 2 pi f of t e to the minus I n t. And so I n theta, so what is this? This is like e to the I n and theta minus t dt. So we're just working, grinding through, and we want to eventually we want to isolate like a sum of this times e to the I n theta. The problem is I have theta minus t instead of theta, so I want to make a change of variable, maybe u, or maybe like s equals theta minus t, so ds equals minus dt, and then rewrite the integral. And the integral becomes what? So if t goes from 0 to 2 pi, s will then go from theta to theta minus 2 pi, and f of t becomes t is equal to theta minus s, right? And I get e to the ins, and then dt becomes minus ds. Now, because this is a periodic function, Product of periodic functions. This is periodic in S. And it's 2 pi periodic. So if you integrate a periodic function over its period, the answer does not depend upon where you begin or end. So in other words, I can choose any theta. Theta equals 1, theta equals 0, and integrate it from here to there. And I'll get the same result. And so I'm going to choose theta equals 2 pi. So integrating from 2 pi to 0. And since I'm just integrating over one period of the periodic function, it doesn't matter. And now in exchange for the negative sign, I'll rewrite that as 0 to 2 pi. So this is already starting to look quite good. And now integrals are linear, so I can bring the sum inside the integral. This is an infinite sum, so if you think about it, an integral is a limit, and an infinite sum is a limit. So what I'm about to do to bring the sum inside is just switch the order of those limits. It's an analysis problem for when you can do that, but when the series is absolutely convergent and when this integral is in L1, which it is, so-called absolutely convergent integral, you can make the switch. So I'll bring the sum inside, and I'll pull the constant out. So I'll take 1 over 2 pi. I'll do integral from 0 to 2 pi. I'll take the sum now, r over capital R, absolute value of n. And I'll pull out this constant to the front of the sum, so f of theta minus s. So I'll have to rewrite that. Times the sum of r over capital R, absolute value of n, n and z, e to the ins, ds. So that's all legitimate. I didn't pull this out in front of the integral. This stays inside the integrand. But I moved the sum to the inside, and this is a constant with respect to n, so I could factor it out from the sum. I used the limit law to pull it out of the infinite sum. And all that work was designed to do one thing. It was to get this expression by itself, which I did. And so now this is equal to our expression that we derived. Now this is equal to our expression that we derived. And this is 1 over 2 pi. Integral from 0 to 2 pi. F of theta minus s times what? So I need to plug in this number, r over r, into our formula. You got it. Cosine s, right? Oh, yeah. Plus r over r squared ds. So now we're getting somewhere. What's the question? No, it totally is. You're right. It is a convolution. Yeah. I'll put some terminology down. So this PR of S is this formula that we saw. Is 2 times r times cosine of s plus r squared. So this is called the Poisson kernel. So we've put in, what we've put in here is P of R over R of S. So this is P of R over capital R convolution with F of theta. You plug in theta, and there's the output. That's the definition of convolution over the circle. So if you want to solve the Laplace equation on a disk of radius capital R, you convolve with the Poisson kernel of R over that radius. And that's what you get. It's also true that convolution is symmetric. So I'll make this look like the book formula for you. So you could rewrite this as one over 2 pi, integral from 0 to 2 pi. You could rewrite this as f of s. It's basically putting this with s and that with theta minus s. So it's just doing the change of variable we just did, but again. And then, so this becomes theta minus s. And if you also multiply and divide by r squared, you end up with capital R squared minus r squared over r squared minus 2 little r capital R cosine theta minus s plus little r squared ds. That's the official Poisson integral formula. This is u of r theta. And it satisfies the property that when you plug in capital R, you get back your original function. And there's no infinite sum in there. So this is like a great success of separation of variables. If you like, and the immediate application of this is that if you plug in r theta equals 0, 0, this is like the temperature at the origin. So what do you get? You get 0, 0, 0. This over that is equal to 1. So you see something that we call the mean value property, which is to say that the temperature at the origin is the average of the temperatures at the boundary, which is always true for steady state solutions. And that's true not just at the origin. So even if you had some funny boundary, you had Laplacian u equals f, you pick any point, x naught, and draw a small circle around it. U of x naught will always be the equal to the average of u integrated around that small circle. So there's a more general version of the mean value property that you learn in advanced classes, but it makes total sense. If you're at that steady state solution where the heat flow has already settled down, it averages you out. So there's not like a heat discrepancy in any one direction that's pulling your temperature away from you. is quite nice. Okay. So apologize for going a little bit over, but that's Poisson's integral formula by way of the Poisson kernel.
And what is a kernel?
So yeah, like why do we call these things kernels? They're basically these functions that generate solutions to PDEs for us by convolution. I don't know that I have an official definition for the word kernel, but that's usually what, you know.
So they're just like expressions that come up frequently.
Well, not just an expression that comes up frequently, but an expression that's used to solve a PDE through convolution with your initial data.
I don't really get this last
Well, let me officially end class. So thank you, everybody, and take care.